So we were about to do an example of the derivation of a state space model for a circuit from its linear graph model, right? So we're starting with the linear graph, which we learned about how to do last chapter. So the linear graph model has the coordinate arrows already given for this circuit, so it's already drawn as well. So it's got two resistors, a capacitor, an inductor, and a voltage source, right? So this is actually the same linear graph that we used in the last lecture to sort of work an example on for the normal tree, right? So let's go ahead and go through our steps. So all the steps are up here, right? So maybe I'll delete the check marks. So the first one is to draw a normal tree, right? So 1A is to draw the normal tree. And we have our graph here. Could change colors probably, just so that it's a little bit more clear. So what's the first step when we draw the normal tree? So we have the two rules, right? We got to get all the nodes, and then we got to make sure there are no loops. So we tend to stop actually highlighting the nodes because we know they're all going to be in the normal tree eventually, but it's good to start doing it the first time. And then the next thing that we do is we go through a list in descending order of priority for inclusion into the normal tree, right? So the number one priority is across variable sources, right? And we've got one here. We've got the voltage source. The next one is A-type energy storage elements. We've got the capacitor. The next one is D-type elements. And we can't take R1, remember, because it would create a loop. So we have to take R2. And we would then take T-type, but that would create a loop too. So there's there are no more edges we can include into our normal tree for this graph. Cool. So switch back to black here. So there's our normal tree. Good. So the next step. So A, normal tree. Oh, thought I switched back. Identify primary and secondary variables. Okay. So primary, and then we'll do down here secondary. So primary variables are defined as being across variables on elements in the normal tree, so on branches, and through variables on links. So across variables on branches would be VS, VC, VR2, and then through variables on the links would be IR1 and IL. It's a really big comma. Secondary variables are exactly the opposite of that, so I just flipped these bits, if you will. IS, IC, IR2, VR1, and VL. Great. 1C is next. select the state variables to be across variables on A-type branches and through variables on T-type links. So A-type branch, so we've got state variables. We've got an A-type, because the capacitor for an electronic system is the A-type energy storage element, right? So it's an A-type in the normal tree, so it's a branch in the normal tree. So we take its across variable, VC, and there's a T-type here that's in the links. So we take its through variable to be a state variable, IL. Great. So this tells us that the order of the system is what? If you have two state variables, we said the number of state variables is equal to the order. So it's a second order system. Good deal. Okay. Good. So that was 1C. Define the state vector. So D is to define the state vector x, input vector u, and output vector y. So the state vector, 1D, state vector x is equal to, we'll make VC the first one and IL the second one. But we could have chosen the opposite order. It's arbitrary. Okay. And what about the input vector? What are our inputs in this model? Vs, right? Just the voltage source. So there's only one, so just Vs. So 1 by 1. All right, so 1 vector. And the output, we have to go back to the problem statement to look for the output. There was no clearly defined output in the problems. Like there was no like output leads saying V out or anything like that. So we have to go back and read this. It says with outputs, and it explicitly asks for outputs IL, IS, and VR2. So we'll just write that. Output being IL, IS, and VR2. Okay. So those are our state, input, and output vectors. Okay, so we've got that 1D done. E, write an elemental equation for each passive element. We're used to doing this. So 1E, you can draw a little table. So let's do C, L. You don't have to, but I like to put the energy storage elements at the top of my table. And that's mostly because we're eventually going to end up with those equations. Those are the elemental equations that will become our state equations eventually. I like to keep them separate from everything else. I also like to put them in the same order that I put the state vector in, just to keep things nice and straight for me. So CL and then R1 and then R2. Those are the 4 elements. And the elemental equation for a capacitor, I should say elemental equation. So for a capacitor, the elemental equation is dVc dt equals 1 over CIC, right? the elemental equation for an inductor, dIL dt equals 1 over L VL. For a resistor, we have just Ohm's law, right? VR1 equals IR1 times R1. And for the other resistor, VR2 equals IR2 R2. Now, we did say so something that I didn't put in the directions explicitly, but something that will become apparent in a minute, is that it makes sense to solve for the primary variables in the elemental equations. The primary variables are always the time derivative variables for the energy storage elements, but they're they can be VR or IR. They can be the across or through variable for the resistors or for D-type elements. So we are going to want to solve for the primary ones. So VC is already like this. IL, the elemental equation is already solved, so VC is already solved for that. IL is already solved for that. VR2 and IR1 are the two that we want to solve for. We want to solve for primary variables. So IR1 from this equation is equal to VR1 divided by R1, right? And VR2 is already a primary variable, so we don't have to change this one. You don't have to do this step. This step isn't necessary. It just makes it a little bit more convenient when you do a later step in the process. In part 2 of the process, it's a little bit more convenient to have it this way. So if you forget to do this, as I usually do, no big deal. So then 1F is the continuity equations. So write the continuity equation for each passive branch. So branch, right? So branch in the normal tree by drawing a contour intersecting that and no other branch. Solve each for the secondary through variable associated with that branch. Okay, so passive branches, so we have 3 branches in our normal tree, right? We have an active branch, the source, and then we've got 2 passive branches. So we need to write a continuity equation for each passive branch. So the first one that's pretty easy to do is to draw a contour around this node, and that cuts through a single passive branch, and that's what we want. So this is a continuity equation that you would write for this would be all of the current going in to the node is equal to all of the current going out of the node, or out of the contour. So my IR2 is going in, must be equal to IL coming out, right? So continuity. So you're going to need one for, and I like to draw a little table here too. So you're going to need one for R2, and you're going to need one for L, right? That's the other passive, or no, one for C. That's the other passive branch in the normal tree. So R2 tells us that IR2, everything going into the contour we just drew, is equal to IL, everything coming out of the contour that we drew. Okay. The next equation, continuity equation, is going to come from drawing a contour that intersects only C. We can't do this contour. And why is that?
Because it connects through 2 branches.
Yeah, because it cuts through R2, which is also a passive element in the normal tree. So that's not what we want. It's okay if we do this node down here, but I wanted to show one that was maybe a little bit different. This one. So that's totally valid. It just goes through one passive element in the normal tree. And so for the capacitor, we see that it's coming out of the contour, right? So it must be, the current going into the contour must equal the current coming out in C. So we can say that IC has to be equal to IR1, which is going in, minus IL, which is going out, right? So IC must be equal to IR1 minus IL. Could have just summed everything going in and said everything going in is positive and then solved for IC, but like I told you, it's nice to skip that step and have it solved for the variable that you already want solved for. So that last part of 1F, which says solve each for the secondary through variable associated with that branch, that's what we've done from the beginning. So the passive element the through variable, no. The secondary variable associated with R2 is IR2, right? So we wrote its continuity equation already solved for IR2. That's why we do this shortcut method. IC is the secondary variable for the capacitor, right? And we want to solve for that, and so that's what we've done. We've already written it down in a form that has it solved for IC. So we sort of skip the step where we have to then solve for the secondary variable. That's why I like to do it this way, because you end up having to do one less step. One fewer step. Okay, so then 1G, if you go back and look, it's the compatibility equation. So we have to do one for each link momentarily being placed inside the normal tree or being connected to the normal tree. So there's a loop that's created, and we do a compatibility equation around the loop, just like KVL, right? And so we've got two links here, R1 and L. So if we put R1 in, then we would see that VR1, thinking like a vector here, VR1 has to be equal to VS minus VC. Okay? So we've got R1 and L. So we say that VR1 has to be equal to VS minus VC. Okay. And then the other link, the inductor, L, if we placed it into the normal tree, it creates a loop as well. Thinking again like a vector, starting at the tail of the vector, we have negative VR2 plus VC is equal to VL, right? So we say VL equals negative VR2 plus VC. Any questions so far? So we've got step one is done, right? If we go back up here, we've got now the continuity and compatibility equations. So that just leaves part two, which is to eliminate variables that are not state or input variables and their derivatives. So part A, 2A is to eliminate all secondary variables by substitution into the elemental equations of the continuity and compatibility equation. So we've got 4 continuity and compatibility equations, and we can use each of them. They're already solved for their secondary variables, so we can just substitute each of them into the elemental equations and eliminate all of the secondary variables in one step. Now, if we had not done this extra step here and solved for the primary variable for the elemental equation for R1, then we would be plugging in VR1 on the left-hand side of the equation for R1. No big deal. It's just that if you have them already solved for the primary variable, the variable you're going to eliminate, the secondary variables on the right-hand side of the equation. It's a little bit nicer that way, but it's really 6 or half a dozen or whatever. So let's rewrite our elemental equations, substituting as we go the continuity equations. So 2a, we have our table CL R1 R2, and we have dVc dt equals 1 over c. And it would be IC, but we're going to look for the continuity equation for C. It's solved for IC, right? So we can substitute in IR1 minus IL instead of IC. So IR1 minus IL. Similarly, we have dIL dt equals 1 over L, and it was VL, right? But we're going to have a compatibility equation for VL right here. It says that VL is just equal to, I'm going to flip these, so it's VC minus VR2. VC minus VR2. Good. And R1 said that IR1 equals equals VR1 over R1, right? So I'll write 1 over R1 times VR1, which we have a compatibility equation for VR1 right here. So VR1 is equal to VS minus VC. Good. And finally, we have our VR2 being equal to R2 times IR2, but we're going to substitute in the continuity equation for R2, that IR2 is equal to IL. Okay, so we're down to 4 equations now, and we have a second order system. So we're going to end up with 2 equations in the end. So the order of the system ends up being the same as the number of equations you need at the end, so we still need to get rid of 2 equations. At this point, this is the part where sometimes it can get a little bit hairy, although everything up to this point was completely deterministic. This is always going to happen. There are not going to be any major surprises thus far. Now we have to get rid of 2 variables from these 4 equations. What tends to work well is to try substituting. So oftentimes these D-type elemental equations can be directly substituted into the elemental equations for the energy storage elements to eliminate those remaining 2 variables. It doesn't happen every time, but it does often happen. So let's let's just look at this for a minute and see that we have Vs, we have Vc, we have IL on the right-hand sides of these two equations. These are all, so they're an input variable and then two state variables. Vc is a state variable, IL is a state variable. So if we just substitute these into these equations up here, eliminating IR1 and VR2, we get rid of them. So I'm going to write substituting the R1 and R2 equations into the C and L equations. We have, so I'll rewrite C and L. We have dVc dt equals 1 over C. Instead of IR1, we're going to say 1 over R1 times Vs minus Vc. And so that was substituting the R1 equation in there. And the next term is minus IL. Good. So let's take a look at this for just a moment before we move on. This is an input variable, right? This is a state variable. This is a state variable. So that equation is a state equation. It's ready to go into our vector state equation that we'll write in standard form in a minute. And the next one is dIL dt equals 1 over L times, we need to substitute this R2 equation in for VR2. So we have Vc, which is a state variable, minus R2 IL. Great. And this one has Vc, a state variable, and IL, a state variable. So it's ready to go as well. And they're already solved for the first derivatives. So we're ready to put it into the standard form. So this is 2b we've completed now. So we did A, B. So now we need to write the result in standard form. So let's remember what standard form looks like, right? So write in standard form, which is dx dt equals ax plus bu, right? So we know what x and u are. We just need to write a and b from these state equations that we've found. So the way I like to do it, and everybody can sort of choose their own way of doing it, but in order to keep track of where you are, it's kind of nice, like what was the order of your state vector? Sometimes it's easy to forget. So what I usually do is I will write out x or dx dt explicitly. So I will write dvc dt. I can make this a little bigger. I need to cramp it in. And then dIL dt. So this is the time derivative of the state vector, right? So the state vector was VCIL. So you take the time derivative. Take the time derivative of a vector, you just take the time derivative of each of its components, right? So that's what we've got. on the left-hand side, so dx dt equals, the A matrix is an n by n matrix, right? So in this case, it's 2 by 2. So a 2 by 2 matrix times the state vector, right? State vector is just VCIL plus the B matrix, which has to be 2 by something, and we have only 2 by the number of inputs. We only have one input, so just 2 by 1 times U, which is just VS, right? So all we need to do now is fill in the A and B matrices. This is our A matrix here, and this is our B matrix. Oops. So the first equation, the first row is the first equation. So we've got dvc dt equals something in terms of state variables and input variables, right? So VC is the first, so if you're doing matrix multiplication, you're taking this row and multiplying it by this column, right? So the first term here is going to be multiplying VC. If we look at VC in this equation, we could explicitly write out what that is, right? So let's go ahead and do that. Let's write this again with the VC component VC term by itself. So we have 1 over R1C, and it's negative, right? So negative 1 over R1C times VC. And then let's write the IL term. So that's just negative 1 over CIL, right? Minus 1 over CIL. And then finally, there's plus 1 over R1C times VS. Let's do this for the other equation as well. We have 1 over L VC and negative R2 over L times IL. Once you do several of these, you probably don't need to rewrite the equation explicitly like this, but it's good to do first time. So your VC term is right here in the first equation, right? So negative 1 over R1C times VC plus negative 1 over C times IL, right? And that comes from this term, negative 1 over C times IL. Finally, there's a VS term as well, so plus 1 over R1C times VS. So that's the first equation, and we've got half of our A matrix and half of our B matrix. So the lower equation, we have dIL dt equals VC's got a 1 over L coefficient, so 1 over L, and IL has a negative R2 over L coefficient. And there's no VS here, right? So you could say plus 0 VS, right? If you wanted to. You don't have to. And that gives us a 0 VS in the B matrix. So that this 1 over L goes in here. This negative R2 over L goes in there. And then this 0 goes in there. And that is the standard form of our state equation. Okay? Woo! This is the hard, and that was like, this is a great accomplishment. Good for us. Okay, now is the easy part, 2D, which is to express the output variables in terms of state and input variables using any of the elemental continuity and compatibility equations. So, it's important to, I think, take this a little bit slowly. So that the output vector we defined was IL, IS, and VR2, right? So we need to write these in terms of our state and input, state and input variables. So IL is already a state variable, right? So I'm going to actually just rewrite this. IL, IS, and VR2 down here. So IL, IS, and VR2. So we need to write them, so we need to say equals something in terms of state and input variables. IL is a state variable, right? So you can just write IL equals IL if you want. IS is the current coming from the source, okay? And you may or may not remember that when you have a voltage source and a cross variable source, well, a voltage source, specifically in this case, and you have a drop this way, it supplies current actually in the opposite direction. I don't know if you guys remember that. It's a little bit of a weird thing that we talked about a while ago. So its current, IS, is going this way. So if you did a little contour around that node and did a continuity equation, or just thought in terms of KCL, which is equivalent, then we see that IS is just equal to IR1, right? Okay, so IS is going into the node, IR1 is coming out. So IS is equal to IR1. It's equal to IR1. And now IR1 is not a state variable, and it's not an input variable, right? So we need to write it in terms of a state or an input variable. And we could go through and just ad hoc use continuity equations, compatibility equations, see if we can transform that. But let's look through, because IR1, we solved for IR1 as part of this process. And usually, as you go through, you've done that for the output variables. So it's kind of nice to just scan through and see, did I solve for this along the way? And in this case, we absolutely did, right there. So IR1 is equal to 1 over R1 Vs minus Vc, an input Vs and a state variable Vc. So IR1 is just 1 over R1 Vs minus Vc. Oops. 1 over R1 Vs minus Vc. Good. So state variable and input variable, so we're done with that one. And now our third output is VR2, which is not a state variable, and it's not an input. So VR2, let's go scan through and see. We solved for it right here, right? So we don't need to do anything special. Just use that, R2 times IL times IL. And we've got these three expressions for the three outputs. So we've got just standard form left. So the standard form of the output is y, so let's see, standard form, which is y equals cx plus du. So we could write it as, if we wanted to, we could write it as IL, IS, and VR2 equals some C matrix times x. So the C matrix has to return a 3 vector when it operates on x. And x is a 2 vector. So that means that C has to be a 3 by 2 matrix, right? So, and this is a 2 vector, VC and IL, X vector, plus the D matrix, which has to return a 3 vector when it operates on U. So it has to be a 3 by, and the input is a 1 vector, so it's a 3 by 1 times the input vector, which is VS. Okay. So now we just need to fill in these matrices. This is the C matrix, and this is the D matrix. And so we have the first expression is IL. So IL is just equal to IL, right? We want to take 0 VC, 0 times VC. We want to take 1 times IL, that's what we want to return, and we don't need any VS. Right? So that was the first equation up here. I'll put the check over here. So IL equals IL. This first row now says IL equals IL. Right? Nice. The second row is going to express this second equation, which says that IS is equal to negative 1 over R1 VC. And so times VC, and then there are no IL terms, right? So 0 IL and 1 over R1 VS. Okay. Finally, so we did this one. And then finally we have to express this last output equation. VR2 is equal to R2IL. So that means that VR2 is equal to 0 VC times R2 IL plus 0 VS. And that is our output equation in standard form. Okay. Are there any questions? Yes.
In matrix B?
Yes.
Is that a 0 or a D?
Oh, it's a 0. Yeah. Any other questions? So this process, go ahead.
The state space model is the both of the two matrix equations.
Yes, so this is the state equation, and this is part of the state model. So state equation. And this is the output equation, which is the other part of the state space model. So when you've got your state equation and your output equation, you have a state space model. So we've now gone from a linear graph model all the way to a state space model. And yeah.
And what does the state space model accomplish?
So we're going to talk about how to solve it in different ways. But once we solve it, we get to know what our states are for all of time, and we get to know what the outputs are for all of time. So we're going to solve for effectively these variables for all of time. So remember when we would do circuit analyses and we would say, okay, here are the initial conditions, solve for what the voltage out is going to be for all of time. We can do that same thing here, but we can do it in a way that's more systematic and that lends itself to simulation and high order systems. So yeah, effectively that. It's a differential equation that we can solve. And it's in a form that's nice. So. Yeah. All right.
Thank you.
Sure.